Hi, my name is Achuta Kadambi, and I'm an associate professor of electrical engineering and computer science at UCLA. I joined UCLA in 2018 after completing my PhD in AI at MIT. There, I recognized that AI can do a lot of stuff, but it struggles to compute things that require measurement precision or exactness. This inspired me to build my group at UCLA around the development of next-gen AI technologies where exactness is not just desired, but it's a design constraint. Mission-critical AI, or machine learning, is what we like to call it. One example focus of our group lies in perception, giving machines the gift of sight, kind of like how self-driving cars drive. Machine learning has transformed perception, but it tends to hallucinate visuals. What do I mean by this? Well, when AI is geared to produce an image that you think is real, it may not quite be that image that is real. This might not be a problem for our enjoyment of a Hollywood movie, but hallucinating outputs is inadequate when aiming for exact estimates of physics. For example, taking a picture and getting someone's heart rate, taking a picture and estimating if a bridge is going to collapse. A key goal of my lab is to make sure that we can robustly estimate these physical quantities from data, and to do so we use the power of machine learning and we blend that with laws from physics to get AI to work without hallucinations. Today's machine learning algorithms, by contrast, they excel at tasks like generating content, classification, estimating which movie you'd like to watch, but they lack that physical interpretability. A model might say a face looks happy. You might classify it this way, but it can't quite tell you if a person's skin is layered with makeup. Are they wearing 200 microns of sunscreen on top of their skin? Or is their heart beating at 75 beats per minute? In principle, if we could measure or compute these quantities, it could enable us to build useful devices for medicine and healthcare where you can, in non-contact form, estimate these quantities just from images. Much of the work in our lab aims to tackle these problems by combining physical laws of the universe that we take to be true with a black box machine learning model. This enables us to estimate accurate, exact quantities from standard video inputs. An example that I'll return to is estimating heart rate from video by learning the subtle color modulations in skin tone. This is rooted in blood perfusion. What do I mean by that? Every time our heart pumps, there's more blood that's going into our blood vessels. That blood can be seen under the skin, and these changes cause a tiny bit of color change that a video camera could in principle pick up. By combining this measurement with AI, we were able to estimate heart rate in a manner that's accurate enough to be used in clinical medicine. So in particular, we validated our approach in site environments like UCLA Hospital, testing on 100 subjects using consumer-grade cameras from smartphones. The end result was our system estimated human vitals, such as heart rate, such as other factors, oxygenation, in a totally non-contact manner, and in some cases was less than 5% error compared to clinical equipment that had direct contact with the human subject. So that means, if I return to the heart rate example, you can extract heart rate just with a cell phone camera, not even touching a patient, in a manner that's almost as accurate as a clinical device that someone is wired up to. Our UCLA lab has filed a few patents in this domain for the research. We'd like to graciously acknowledge support from the National Science Foundation, NSF, as well as DARPA programs. In the future, we envision a world where machine learning acts as a scientific co-pilot, unlocking insights about the physical world from data and helping scientists invent for mission-critical settings. To continue to advance this goal, our aim is to scale our work with partners, both existing partners and hopefully new partners, to bring our AI technologies to mission-critical settings where exactness is not just desired, but demanded. Thank you.